Oh, wait, it's this one?
Yeah.
Okay.
All right, so
Okay. Take it away.
introduce
Oh, no.
everything.
What's going on? There we go. All right. Hello, everybody. I'm Lucy, and this is Vitahe, and we'll be talking today about relating the structure to function in whey protein subjected to pretreatments. So to give you a refresher, we've talked about this a bit in class, but there are two main proteins in milk. Those are casein and whey. So casein makes up about 80% of that, and whey is the remaining 20%. And casein is characterized by its open structure, which makes it very heat stable, compared to whey, which is a very compact globular structure. So that means it has a lot of secondary structure, so it's susceptible to heat denaturation. And casein, again, is characterized by hydrophobic and hydrophilic patches, which make it a great natural emulsifier, whereas whey is known for its highly hydrophilic surface, so it's very soluble, making it great for protein beverages. And we'll be focusing on whey today, so I'm going to get into the main constituents of that. So there are two ones we'll talk about, beta-lactoglobulin and alpha-lactalbumin. So beta-lactoglobulin is about 50% and alpha-lactalbumin is about 20%. And beta-lactoglobulin is primarily beta sheets, but also contains one short alpha helix and two disulfide bonds and a free sulfhydryl group. And that free sulfhydryl group is really important for initiating reactions with other proteins such as polymerization, whereas alpha-lactalbumin, on the other hand, is mostly alpha helices, so it denatures at a lower temperature than beta-lactoglobulin, and it contains four disulfide bonds but no free sulfhydryl group. Now to just look briefly at an overview of the two papers we're looking at. Article 1 focused on whey protein isolate and looked at the effect of temperature and pH pretreatments, whereas Article 2 was looking at polymerized whey protein isolate and concentrate and the effects of denaturing heat treatments and concentrations of protein solutions. And they both measured functionality in terms of emulsion activity and stability. So Article 1 was titled The Effect of pH and Temperature Pretreatments on the Physicochemical and Emulsifying Properties of Whey Protein Isolate, performed at University of Saskatchewan in 2015. And basically why they wanted to do this work, they were looking for a deeper understanding of how temperature and pH pretreatments would affect the structure of whey and possibly improve functionality. And their objective was to investigate the emulsion activity index and emulsion stability of whey protein isolates subjected to pH and temperature pretreatments. And the hypothesis was that these pretreatments would essentially change emulsifying abilities. So this is kind of an overview of their experimental design. So they started with 0.1% protein solutions of whey protein isolate. These were stirred for 60 minutes at pH 3, 5, or 7, and then held in a water bath at 25, 55, or 85 degrees Celsius. And then they performed some structural characterization such as circular dichroism, interfacial tension, surface hydrophobicity, intrinsic fluorescence spectroscopy, zeta potential, and aggregate size. And then the functional properties, again, they looked at emulsifying activity and stability indices. So we'll only be focusing on three structural methods here, so I've just listed them here. Zeta potential bioelectrophoretic mobility, surface hydrophobicity using the ANS Pro method that we talked about in class, and aggregate size looking at dynamic light scattering. And the functional methods, again, emulsion activity and stability, similar to how we've described in class. So getting to the first results, for zeta potential, they found the isoelectric point to be between 5.1 and 5.4 depending on temperature. And this is a little bit higher than the reported value of about 4.6, which they attributed to possible different starting materials or slightly different measuring techniques. And they saw a linear decline in surface charge over pH, which would be expected since at pHs below the isoelectric point, proteins will be positively charged, and above the isoelectric point, they're negatively charged. So that wasn't all that surprising. For surface hydrophobicity, their most significant finding was they found a peak at 85 degrees Celsius in pH 5. And this was due to the denaturation exposing hydrophobic groups that were previously hidden in the surface or in the interior of the protein. And additionally, at a low net charge, you're going to get a lot of hydrophobic interactions, therefore. That's the consequence of denaturation. And they saw the lowest fluorescence at pH 7, even compared to pH 3. And they said this was because the ANS probe is anionic, so it has preferential binding with a positively charged protein, and also slight differences to protein conformation just due to those different solubilization pHs could make pH 3 essentially a little bit more hydrophobic in its structure after refolding. And now getting into aggregate size, they were similarly small at pH 3 and 7 due to high electrostatic repulsions. The largest aggregates were at pH 5 for all temperatures, and they were largest between 25 and 55 degrees Celsius due to the coagulation of the beta-lactoglobulin and alpha-lactobumin subunits. And they were slightly lower at 85 degrees Celsius, which is caused because the alpha-lactalbumin denatures, but it has free sulfhydryl groups from denaturation that are then very reactive and will polymerize with each other. So it had an intermediate form. Emulsion activity, there was a drop at pH 5 for all temperatures due to large aggregate sizes we just saw that will hinder the ability of the proteins to migrate to the interface and unfold and wrap around the oil. And emulsion stability was greatest at pH 7 due to repulsion between the negatively charged proteins. There was lower stability at pH 3 compared to 7, again due to some higher surface hydrophobicity of pH 3. So now to get into overall conclusions for Article 1, emulsion activity was negatively correlated with aggregate size. Emulsion stability was also strongly negatively correlated with aggregate size and had moderate negative correlations with surface hydrophobicity and surface charge. Samples that were heated at 85 degrees Celsius performed equivalent or worse than samples that were below the denaturation temperature of whey. And samples at pH 5 had a low surface charge, which led to subsequent aggregation, which would hinder EAI and ES. And now some critiques of the first article. So they didn't have a very specific hypothesis. They just kind of said they thought that these treatments would change emulsifying abilities. So it's really good to have a direction, like do you think it's going to get better or worse with your changes that you're making? Additionally, they didn't prepare their own WPI, so they outsource it. And preparing it in-house would actually give you better control over how it's extracted and if it's exposed to any heat or denaturation beforehand, which would be important for this study. And then also with that, running DSC on an unheated sample of the whey protein isolate that you're starting with would give you an idea of if it's already denatured coming in. Running SDS page would help you confirm how those alpha-lactalbumin and beta-lactoglobulin subunits are affected by your pretreatments and if they are, in fact, explaining some of your structural results. Then using more tables and fewer figures to display the data, I think just helps make it more clear to readers to understand the differences between values instead of seeing a lot of dots kind of overlapping on the graph. You have numbers to work with. Performing emulsification capacity, just kind of give an overview of the whole picture of emulsions instead of just the two assays that they did run. And then considering the effects of the emulsions in a food index or in a food matrix and how those other factors might influence some of these results. And lastly, they mentioned a few times that concentrations could play a different effect between their results and the articles that they were comparing to because they were solubilized at different concentrations of starting material. So looking at some different starting concentrations within one study, I think would really help to explain your results a little bit better. And that's actually what this next paper will kind of start to talk about.
So the next article was effect of heat treatment on physiochemical and emulsifying properties of polymerized whey protein concentrate and polymerized whey protein isolate. The study was conducted considering that heat-induced aggregation of whey proteins may influence the physiochemical and functional properties of polymerized whey proteins. Polymerized whey proteins are the aggregates of whey proteins that are formed when subjected to higher temperatures. Here, higher temperatures typically mean the temperatures above the denaturation temperature of whey protein, which would cause the unfolding and interaction of proteins via hydrophobic interactions and formation of disulfide linkages and formation of the aggregates. The objective was to investigate the effect of thermal treatment on physiochemical and emulsifying properties of polymerized whey protein concentrate and isolate at various temperatures and concentrations of whey protein solutions. Hypothesis was modification in the protein conformation due to heat treatment will influence the physiochemical properties and change the emulsifying properties of whey protein concentrate and isolate. Looking at the experimental design, the samples were whey protein concentrate and isolate. They were dissolved in water to form solutions at concentration 8, 10 and 12% and subjected to a heat treatment in the water bath for 30 minutes at 80, 85 and 90 degrees Celsius. I like to point out that all the three temperatures are above the denaturation temperature of whey protein, which is around 70 to 75 degrees Celsius, thus ensuring the formation of polymerized whey proteins. The structural characterization and physiochemical properties were studied using various methods like determining free sulfidyl groups, fluorescence, zeta potential, SDS page, and transmission electron microscopy. The functional properties that were studied were viscosity, emulsion activity, and emulsion stability index. Some of the methods for structural characterization were determining sulfidyl groups using Elman's reagent, fluorescence analysis, SDS page to further understand the changes in the molecular weight upon heat treatment, and zeta potential to understand the surface charge. Functionality methods were evaluated using emulsion activity index and emulsion stability index, just like in Article 1. Looking at the results for free sulfidyl groups, there was significant reduction in the heated samples, mainly due to the denaturation of whey protein with heating that exposes the sulfidyl groups. As Lucy mentioned, that beta-lactoglobulin has a free sulfidyl group, so such free sulfidyl group are exposed and that undergoes sulfidyl group oxidation and exchange of sulfidyl disulfide bonds, and thus decreases the free sulfidyl groups in the whey protein. Also, the content of free sulfidyl groups was higher for whey protein isolate as compared to concentrate, mainly due to the difference in the protein composition in terms of the ratio of alpha-lactalbumin and beta-lactoglobulin. In the table, we can see that the lowest value is for 10% protein concentration and 85 degrees Celsius heating temperature. And you will continue to see this trend of 10% protein concentration and 85 degrees Celsius for other results later in the presentation too. The fluorescent intensity gives an idea about the surface hydrophobicity, and it increased with heat treatment and higher concentration due to the exposure of more hydrophobic groups from the core of the protein during the unfolding of during heat treatment. However, there was a decrease at higher temperature and concentration due to polymerization induced changes. So as we have discussed in the class, that at higher concentration, the protein molecules are in close proximity to each other and have more tendency to interact and aggregate. These are the results for the SDS page gel. So the major bands that were seen were alpha-lactalbumin, beta-lactoglobulin and bovine serum albumin. There was decrease in intensity higher for 10% protein concentration at 85 degrees Celsius. So this suggests that the whey proteins at these conditions were more polymerized. The decrease in intensity was greater for beta-lactoglobulin as compared to alpha-lactalbumin, again mainly due to the presence of the free sulfidyl group that initiates the polymerization and causes more polymerization. Looking at the results for zeta potential, they were lower for heated sample. This suggests that the net negative charge in heat-induced aggregates was increased upon heating. Again, the same trend can be seen in the table of 10% and 85 degrees Celsius. The emulsifying activity index was lower for heated samples due to the formation of large protein aggregates which are unable to migrate to the surface, the interface and cover the fat droplets efficiently. The emulsifying activity was higher for polymerized isolate as compared to the concentrate, and this was explained using another study which concluded that at pH 7, concentrate undergoes excessive denaturation and reduction in the hydrophobic residues that are available for interaction with oil phase. Again, the same trend for the highest values of activities can be observed here. The emulsion stability was higher for heated samples, and this can be explained using the zeta potential data where we saw that the net negative charge increased for the heated samples, so there was higher electrostatic repulsion between the droplets and that led to more stability. The same reasoning can be used to explain the higher values, stability values for the polymerized isolate as compared to concentrate. To conclude, the polymerized whey protein showed lower emulsion activity index, which can be mainly correlated to the aggregate size and surface hydrophobicity, and it showed higher emulsion stability, which can be correlated to the higher surface charge. The polymerized isolate showed significantly higher emulsion activity as well as emulsion stability as compared to the concentrate. And highest emulsion activity and stability was seen at the condition 10% concentration of whey protein isolate at heat treatment 85 degrees Celsius. So for application that require treating the emulsion at higher temperatures, using this condition would be advisable to using the whey protein isolate to achieve high emulsion activity and stability. Looking at some critiques, so the manufacturers for the two samples were different. So depending on the purification method that they use, the composition and characterization of the samples might be different. They did not mention the exact protein content in the samples, and the solutions were prepared based on the powder content and not the protein content, so it would be difficult to compare the results with other studies. A study of emulsification capacity would be a good idea to understand the application of polymerized whey proteins, and analyzing the statistical correlation would help to further substantiate the conclusions that were made during the study. And as recommendations for future work, it would be a good idea to study the solubility of polymerized whey proteins, because we know that solubility of whey proteins is higher due to its hydrophilic surface, but the heat treatment might affect the structure and thus the solubility of polymerized whey proteins. Also, this study just focused on oil-water emulsion, but studying the application of polymerized whey proteins with other constituents present in food system would be a good idea. Finally, looking at the conclusion and relating the structure and function of whey proteins for both the articles. So both the articles concluded that emulsion activity was most impacted by aggregate size, surface charge and surface hydrophobicity. Article 1 concluded that activity increases with lower aggregate size, lower surface hydrophobicity and lower surface charge. However, Article 2 concluded that emulsion activity increased with lower aggregate size, higher surface charge and higher surface hydrophobicity. With respect to emulsion stability, for both the articles, it was most impacted by surface charge and surface hydrophobicity. It increased with lower surface hydrophobicity and higher surface charge, whereas for Article 2, it increased with higher surface hydrophobicity. So the differences in the conclusions between the two studies could be mainly attributed to the differences in the whey proteins samples, the concentrations, the conditions that were tested, and finally the amount and type of the oil that was used to form the emulsion.
Now we're open for questions.
Thank you. Okay, questions? Wow, one at a time.
I have questions toward the second paper.
Mm-hmm.
So why they add the reducing agents to there's like to move to all the samples to compare what like the SDS page. So if they compare about the polarization, they don't need to add the reducing agent and they can compare. Why they just have the samples that adding the reducing agent instead of have two samples that do not, one is non-reducing one is reducing one, or they have.
No, they just tested the samples with the reducing agent, like all the samples with the reducing agent. I'm guessing they wanted to look at the differences and individual subunits and not just the entire whey protein.
So
and
did they add the reducing agent?
beta mercaptone.
When?
Okay. During the testing, like once the solution was formed, and just before analysis, using.
So they add the reducing agent? I missed that.
Yeah.
Is that what you saw?
Mhm.
Yeah. So before testing of aggregate size?
Yeah.
For SDS page?
Yeah. SES
Yeah.
page.
Oh, okay,
Yeah,
not for
that's-
everything
No,
else.
No, no.
SES page. So
Yeah, that would be all.
yeah. So
Yeah,
she's
so go to the gel. Actually, I have a question about that. So, how did you reach? Actually, I had the same kind of question. If they're testing and the reducing,
Mhm.
how did you get to the conclusion of aggregates were formed?
Yeah, I was.
The aggregates.
Yeah, you were talking about,
Yeah,
you
because-
concluded that there's more aggregate.
Because of the
Form.
decrease in intensity.
Intensity of the bands?
Yeah,
So
they
they
compared it with the
didn't
native.
load based on protein content
No,
when they loaded their samples?
no.
But then when they reduce, they should everything socialize.
So, right. Yeah. So they have mentioned the decrease in intensity for as compared to the native samples for the bands, but they haven't really explained what like the reduction, why the reduction happened, or yeah. So they
Yeah,
just
that is not a
mentioned, yeah.
correct,
Uh-huh.
they can't make that conclusion
Conclusion, right.
based on reduction of
Mhm.
intensity of the bands, because supposedly when you add SDS and when you add beta-recaptoethanol,
Mhm.
you're reducing everything and solubilizing everything.
Right.
So the difference in banding
Mhm.
should not be there unless they didn't load based on protein content. In order to see polymerization, they should have run it without reducing.
Interesting.
Yeah. So what, well, on that question, what else do you think they could have done to actually measure the aggregation or extent of aggregation in both particles?
Well, they could have, for this one, they could have just done aggregate size, which would tell them a little bit, kind of like
Mhm.
similar to Article 1.
Yeah.
I think that would give a more clear indication for that one.
Yeah.
One thing they did do that we didn't show was transmission electron microscopy,
Yeah.
which kind of gives you a very qualitative overlook at aggregation, but not very,
Mhm.
you can't tell maybe smaller differences, but they did see that it was more aggregated in whey protein isolate versus concentrate, so you could kind of look at that one. Another aggregation.
Yeah, I would say the HPLC MALS method that we have
Mhm.
studied during class, that would
Size
also,
exclusion,
size
yes.
exclusion would help for,
Yeah, because
Yeah.
especially they reach two different conclusions,
Mhm.
opposite conclusions in some cases.
yeah.
Because they said one said higher aggregate
Mhm.
size, one said lower
Lower,
aggregate
yeah.
size, but are we comparing apples to apples?
Mhm, yeah.
Yeah.
Not. Okay, I have a couple more questions, but any other questions? I would like more interaction from the class, even though you've done your participation points. The idea of a presenting is not to check a box, and it's kind of learning as well. So if there's something does not mesh with the class information, this is when we want to discuss it. So, nothing? Okay.
I guess for both of you guys, what future direction would you take both of the papers, the results from both of the papers with food applications? With the information that you learned, how to apply it?
So,
I guess I was thinking when I was reading them more about like the processing conditions down the road and how that would influence like what type of or how high of a concentration you could use if you had to heat your sample, and what would be the consequences then of any kind of product you were making with emulsions.
yeah.
So that's mostly the second paper, I guess.
For the article 2, I'll say that I was more looking at the temperatures. So, since the stability increased even with polymerized whey proteins, so I think using higher temperatures to increase the stability of emulsions would be a good idea.
And I thought it was interesting too because at least when I read it, I thought the first paper was talking more about kind of how you'd want to denature the or the structure of whey to kind of get it to be a better emulsifier, but they really didn't find that. It like decreased when it was denatured, so maybe there's like a sweet spot around like 60 degrees or something that they could look at as being like the right conditions to slightly denature it, but not over denature it and make it a better emulsifier that way.
Yeah, that's where I was confused a little bit with these two articles. It's like, why did they specifically look at aggregation and how it impacts emulsification? So what was their ultimate goal?
Yeah, I thought it was to get a better emulsion out of it, but then they really they proved that basically you shouldn't treat it, it seemed like the very modest conditions of like a pH 7, 25 degrees Celsius whey protein isolate was the best. So it seemed like a failure in their design almost, or maybe they weren't testing the right things when they set up.
Yeah, and what's really also confusing is it's two different groups of people
Mhm.
that looked at similar
studies, yeah.
things.
And like that, I think the paper, article 1 was from 2015 and so 2018, but 2018 did not cite anything regarding that paper still, like, yeah.
Mhm.
But the article 2 did use the pH 7, and which was seen to be a good pH in the first paper, yeah.
So nowhere in their justification did they explain why they were just targeting emulsification in terms of forming aggregates.
No, it was very
Yeah.
brief in their explanation of why they were doing the work. It was kind of just that they saw, or like past research had seen that pre-treatments could change structural abilities. And they mentioned like the different functionality components you could measure, but didn't ever say why they were looking at emulsifying specifically or what they thought might happen because of the changes.
Yeah.
So yeah, that was a major flaw in their paper design, I guess.
The article 2 also looked at viscosity, but so I didn't include it
Yeah.
here, but it increased with concentration and increased with temperature.
Yeah, go ahead.
So when you go back to the second paper, emulsifying activity index, we see for WPC 90 degrees and WPA
Yeah.
90 degrees.
Mhm.
For WPA it hasn't decreased a lot in
Yeah.
comparison to 85, but for WPC 90 it has decreased from 21 to probably 3.
Right. Mm-hmm.
What do you think?
I think the results, so the explanation that they used from other study, which concluded that it undergoes excessive denaturation. The concentrate undergoes excessive denaturation at higher temperatures. So that could be the reason due
Let
to
me see if I understood your question, Heidi. You were saying from here to here you see
Yeah.
a lot of reduction
Yeah.
from 85 to 90.
Yeah.
But from 85 to 90 you don't see that much
Yeah.
reduction.
Yeah.
So I think that this explanation that they say that concentrate undergoes excessive denaturation as compared to isolate at pH 7, and this conclusion was used from some other study. They have cited an other paper there.
So,
But why?
But
But
yeah.
why?
Yeah, but why?
but why? Okay. WPC has higher concentration of alpha-lactalbumin to beta-lactoglobulin more than WPI. WPI have higher concentration of
Higher concentration beta lactoglobulin.
beta-lactoglobulin.
Mhm.
And, okay, I'm trying to
Yeah.
think
Yeah,
how they got
speak it
that.
through.
And in WPC, since you have higher alpha-lactalbumin, it's more prone to denaturation and it has a lot of SS linkages.
Mhm.
So if you have a free SH group, it might cause reduction and then what do you call it, disulfide interchange
Mhm.
among different proteins
Mm.
more
Mhm.
so than what we could see in WPI. That could be it, but again, can we trust? First of all, can we trust this is the correct data?
Right.
Second, they didn't really do a good job explaining it, not you, but that.
And it really changed from that, if you compare across the table from 10% to 12%, WPC 85.
Yeah.
So for 10% it is around 21, but for 12% it is around 3%.
And then it
Yeah.
goes up to 5.9.
Yes.
Yeah.
Like if you compare between 10 and 12%, it is
Mhm.
8, 10, 12, so it's 17, 21 and then down to 3. But we don't see that for 80 degrees, we don't see that for 90
Yeah.
degrees as well.
Yeah, that one had a kind of didn't follow the trend, if you can call it a trend at
It
all.
does follow the trend. But that's
Yeah.
when you question the data
Yeah.
and see how much is this data true.
Right.
Yeah, because we can throw out a lot of theories trying to explain it, like assuming that their method is correct.
Like looking at all the critiques.
Yeah, yeah, but it's good to think about these.
Yeah.
Good to think about when you guys publish your work. Does your data make sense?
Mhm.
I think that I had it answered along the way.
Have it answered?
Yeah, I think that your discussion answered my question.
Okay.
One more regarding the first paper at least. We don't really see any change in the acidic pH or the neutral pH for any heated sample.
No.
Uh,
Yeah, they said
What would you think for
why there
even-
wasn't a change.
Yeah.
I guess just because. Sorry, go ahead.
No, for zeta potential surface hydrophobicity and emulsification properties. For everything acidic pH or the neutral pH, we are not seeing any change. Does that mean the temperature is not going to affect?
Yeah, so they kind of were saying that in this case, the surface charge had more influence rather than it being like hydrophobic because of the denaturation. So that was like the dominant effect when it was removed from its isoelectric point, but at its isoelectric point, the hydrophobicity also came into play and kind of like amplified the effect of the net charge of 0. So like you didn't see those big differences with the denatured temperature versus like the 55 or 25 degrees Celsius. Does that kind of make sense? Or it's at least something.
It's just very hard to believe that the temperature.
The thing is, there is no discoveries in this paper, I don't think. Because, yes, of course, surface hydrophobicity is going to be high at the
Yeah, I
isoelectric
said,
Mhm.
I said.
So that was another question. I was like, what did they?
Why do you want to perform this?
Yeah.
Yeah, what did you tell us?
You are just stating theories that we already know. So what is the really major finding there? There's no major finding. They just published their work.
Yeah.
Yeah. Okay, we're good. Thank you.
All right.
All right.
Okay, cool.
Yeah.
All right. Let's continue where we left off with milk dairy proteins still. And let's do this exercise together, comparing casein to whey and what we know about their differences and how would that eventually impact functionality. Okay, if we look at the property of the amino acid distribution within casein and whey protein, how are they different? Amino acid distribution, think about polar and nonpolar residue distribution between casein and whey. What's so uniquely different?
Okay, now I'm nervous about my answer.
That's okay.
The casein had the polar ends on most of the subunits, whereas whey, most of the polar was on the outside due to the globular structure and the non-polar on the inside.
You're very close in to the theme here is that we have pouches, like concentrated areas within the casein that you have either polar or non-polar, which makes it very amphipathic or amphiphilic. Whereas in whey you don't have really distinct portions like that, but most of your polar amino acid are on the surface and the hydrophobic residues are within the protein, giving you a regular distribution of hydrophobic and hydrophilic residues. Okay, what about molecular structure? in terms of molecular structure, how do they differ?
Casein would be random form and they like a globular.
Yeah. So we have open random structure, very little secondary structure in terms of secondary and tertiary structure, whereas whey protein is globular. You have well-defined secondary structure of alpha helixes and beta sheets. Okay. What about heat stability and gelation? What's the difference between casein and whey? Which is more stable? Casein is more stable. So stable at high temp up and 140 for 20 minutes. Gelation happens either by using of enzyme, chymosin, or acid as in yogurt, or aged gelation over time, where a beta-lactoglobulin interact with kappa casein over time, and then protein sediment. Whereas in whey, you have thermally induced gelation. It is thermally labile. That means whey protein is more sensitive to heat. It denatures at lower temperature, and then inducing heat gelation. All right, in terms of association, what's the difference? Yes?
Casein is in micelles and whey is naturally in octamers.
So they could be octamers, but micelle, you have the micelle formation in casein with the alpha S1, S2, and kappa casein and beta casein. They all form together a quaternary structure known as the micelle, whereas whey protein can be present as an octamer that's around close to the isoelectric point. Dimer is pH away from the isoelectric point, but if it's too high or too low of a pH, then they form a monomer. Enzyme sensitivity, so the casein is sensitive to chymosin, so that's where we use it for curd formation. Plasmin, which is an enzyme present naturally in milk, it can chop up casein, especially beta casein. Whereas whey protein, given that it is a globular protein, it resists hydrolysis by either native enzymes or endogenous enzymes like plasmin. Plasmin does not hydrolyze whey protein, and whey protein is not that sensitive to chymosin. So it's a globular protein that resists hydrolysis naturally. Obviously, they will be digested by different enzymes, but not as easily digestible as the open structure casein. Surface adsorption, so it is casein are flexible, they're open structures, so they have high surface adsorption, whereas whey, you have low surface hydrophobicity, so you have low surface adsorption for whey protein unless it is denatured. So these are natural, casein is natural emulsifier, whereas whey, you require to denature it or partially denature it for it to emulsify. Okay, solubility. What's the differences?
Whey is very soluble, and with casein has the cap casein making it soluble.
Sure. So whey protein is soluble over a broad range of pH, even at low pH, close to the isoelectric point pH, unless it's heated. Whereas casein, it's sensitive to pH, it's sensitive to calcium, it can be soluble in milk as a casein micelle due to the kappa casein, but then changes in calcium concentration, changes in pH, presence of enzyme can all make it lose its solubility. Conjugation, that means it's not pure protein. It has different units attached to it. Does casein have? Yeah. What? Well, yeah, calcium, but what other groups? So we have phosphorylation and glycosylated. So kappa-casein is glycosylated. Alpha S1 and S2 and beta casein are phosphorylated, whereas whey protein has none of that. What's the difference in sulfur residues? Whey is higher. Whey is higher. So in casein, you have very low concentration. You have maybe one SS linkage in kappa casein and one SS linkages in alpha S2, whereas in whey we have high sulfur groups. Okay, so these differences between the proteins, between casein and whey, present itself in different functionalities. So caseins are usually used as emulsifiers, viscosity builders. If we're using calcium caseinate, like in creamers, cheese imitation for the color, whereas whey, it can be used in protein beverages. It can also be used for gelation once it's thermally induced gelation. So basically different applications for these different proteins based on some of these characteristics. So talking about functionality, so the molecular characteristics that differentiate proteins, these proteins, dairy proteins, that impact their functionality include some of the main ones we talked about. Okay, everybody's tired, no interaction, everybody got their participation points. We lost the participation points sheet. We lost it. So this means we're starting over with participation points. At the beginning of the semester, you were all so active and participating and talking, and now...
It's the weather.
Is it the weather? Okay. Here we go. So interaction with water, surface activity, that means the percentage of hydrophobicity to hydrophilicity on the surface of the protein dictates how it's going to interact with the phases around it, whether it's oil phase or water phase or air. Protein-protein interactions, that means are we going to have disulfide linkages, hydrophobic interactions, calcium phosphate bridges. So all of this indicate or relate to the functional properties of these proteins. So if we look at casein, again, we're emphasizing that it's highly active or has high surface activity due to its amphiphilic nature, because of its open structure. If you remember from emulsification here, it can easily move to the surface. It's an open structure. There's not much disulfide linkages to cause rigidity. So it opens up, gets to the surface, and form protein-protein interactions and form a film around the dispersed phase. So, whereas if we look at beta-lactoglobulin, it is not naturally an emulsifier in its native state because it has low surface activity. It's very polar and highly charged on the surface with very little surface hydrophobicity. So at low pH, for instance, it's compact and rigid. pH close to the isoelectric point, we might have some enhanced absorption to reduce repulsion. However, if we want to make it a better emulsifier, you either partially denature it or you can reduce some of the disulfide linkages within the alpha-lactalbumin and beta-lactoglobulin. If we get 50% reduction in as linkages, we can get easier unfolding and rearrangement at the interface, so enhancing emulsification capacity. In terms of gelation, we talked about gelation, different kinds of gelation for casein. One is the enzymatic coagulation when we break off kappa casein. Once kappa casein is broken off by the by chymosin, then we have interactions with the different micelles forming a coagulum via hydrophobic interactions as well as calcium bridges. The heat coagulation, this is influenced by pH as well as beta-lactoglobulin denaturation by heat, which will complex with kappa casein and with further heat treatment can coagulate together. Acid coagulation, that means with the reduction of pH to the isoelectric point of 4.6, losing the net charge, therefore they come together via hydrophobic interactions forming a three-dimensional gel. And the H gelation we talked about last time in the presence of plasmin hydrolyzing some of the kappa casein, not necessarily kappa casein, hydrolyzing beta caseins, causing thinning and then sedimentation of the proteins, as well as complexing of beta-lactoglobulin has been denatured due to pasteurization of the milk, complexing over time with the kappa casein, again causing gelation. So, gelation of beta-lactoglobulin is mainly thermally induced, and it is a function of the pH of the system. So if the pH is close to the isoelectric point, that means between 4 and 6, then you form opaque, rigid gels, whereas gels that are under higher or away from the isoelectric point, they can be transparent and elastic. If the pH is too low or too high, we're not going to form any gel due to repulsion. But one thing we need to pay attention to is, depending on the pH, the temperature at which gelation occurs is different. So when it's close to the isoelectric point, you have reduced charges. At this pH, proteins are more prone to interact with each other more easily than at pH where you have some charges. So onset of gelation can occur before the denaturation of the protein because you already have low repulsion due to the pH. So you, at temperature 15 to 30 degrees, even below the temperature of denaturation, we can get gelation to occur. However, at pHs that where you have charge, you really need the protein to denature in order to expose some of the hydrophobic residues within the protein for a gel to actually happen. So that is the interaction of pH and heat. It really depends which pH we're trying to form a gel. So we need to decide on which temperature to approach or to reach in order for the gel to form. Gelation is also a function of heating rate. So if the heating rate is really high, like 10 degrees per minute, that's really a high heating rate. So the formation of the gel occurs in a really narrow pH range, below 4.5 and above 6.5. Whereas if the rate of heating is moderate or slow, 1 degrees per minute, you can form a gel close to the isoelectric point. So the idea here, what we want to highlight, or what I want to highlight, if high rates causes really aggregation, quick aggregation and precipitation. But if we're heating slowly, we're allowing the protein to denature slowly and for protein interactions to occur at a slow rate so that you form a gel rather than forming an aggregate that precipitates. Gelation is obviously also impacted by ion strength. So a little bit of salt reduces repulsion, allows for protein-protein interactions. However, high concentration of salt will cause protein interactions to occur at a stronger level. That means less interaction with water, more protein-protein interactions, and more of aggregates and precipitation. Similar to the idea of salting in and salting out. So we can either induce or reduce disulfide interchange. We can reduce disulfide interchange by blocking a sulfide group, or we can induce the interchange by adding a reducing agent like cysteine, for example. Adding a reducing agent promotes the breakage of disulfide linkages within the protein, within alpha-lactalbumin, for example, or within beta-lactoglobulin, and allow the cross-linking or formation of new disulfide linkages to occur across the different proteins. Obviously, protein concentration is a factor that impacts gelation. Depending on pH, we can get to a jelly point of as low as 1% at low heating rate, whereas if we have high pH, or let's say neutral pH, pH 7 or pH 3, we really need higher protein concentration to form a gel. So we have more protein in near proximity of each other to form a gel, since you have charge. Okay, production of the different protein ingredients from milk. So there are so many different ways of producing protein ingredient. The most traditional one is when you produce ranitid casein, or when you're producing the cheese, you end up with whey. Or you can acidify the milk and then separate the caseinates that precipitate at the isoelectric point from the acid whey. And then the acidified casein you neutralize either with sodium hydroxide or with calcium hydroxide. So if you neutralize with sodium hydroxide, you generate sodium caseinate. If you neutralize with calcium hydroxide, you generate calcium caseinate. So these are two different ingredients. So whey, the byproduct of either acid precipitation or rennet precipitation of casein, you get whey. So what you can do here is you can process it in different ways. If you just heat it, coagulate it, you end up with a coagulant called lactoalbumin. It doesn't have much functionality. We'll talk about functionality later. It's mainly used for nutritional value. However, if you take that whey protein and run it through an ion exchange like Agripor does, or formerly the Visco, you get a really nice whey protein isolate with highly functional, highly soluble, highly nutritious product of 92 or above protein. If you take that whey protein and do membrane filtration, ultra diafiltration, and I'll show you a slide about it in a minute. So with membrane filtration, you can get whey protein concentrate. If you add to the ultrafiltration a step of microfiltration later, you can concentrate even more and get WPI, which has over 90% protein. So there are other ways to get the different components of protein directly from the milk. If you subject the milk directly to microfiltration, for example, you can separate casein micelles from whey as well. But this is the most common production of whey protein. When you get the whey as a byproduct of cheese production, which is the most common source of whey, you get the whey run through ultrafiltration membrane. So the membrane that passes through here, the sample goes in, since it's ultrafiltration, the whey proteins as well as phospholipids and large molecular weight protein, that means remain in the retentate. So here you get whey protein concentrate. Concentration of whey protein varies from 34% up to 80% protein. What goes through the permeates, you get a byproduct or a co-product called whey permeate. Has it's high in minerals, high in lactose. It does have some protein still. But then if you take this product and you want to make it higher in protein, you can run it through microfiltration membranes. And here, your whey protein pass through, they become permeate. But what remains here is whey phospholipid concentrate. So your phospholipids are large, they won't go through. So you end up with a co-product that is rich in phospholipid, but it still has proteins in it and some residual lactose. So however, whatever goes through here now is highly concentrated whey protein. So here you got rid of most of the lactose and the calcium ions and other minerals, concentrated proteins and phospholipids there, and then here you're splitting it into a more concentrated protein versus a less concentrated protein fraction. So for uses, so if we look at acid caseinates, so they are really insoluble at pH 4.7. They are low in calcium and phosphate because when you acidify, calcium and phosphate solubilize out of the micelle. So they are, so they leach out of the micelle. So the N casein has low calcium and phosphate. That casein can be solubilized again if we increase the pH. The rennet casein, because it's been treated by enzyme, it becomes insoluble at the pH 7, where you hydrolyze with the enzyme, with the chymosin or rennet. It still has a lot of calcium and phosphate. They are forming cross linkages between the different caseins. And you can solubilize it by sequestering the calcium, pulling the calcium out. You can solubilize the caseins. Both are heat stable. They have good flavor stability, very good nutritive value. They have high PER, protein efficiency ratio. So if we look at PDCAS, they have a PDCAS of 1. So uses, texture, and dough forming characteristics. So they can be added to breakfast cereal to enhance the protein content, snacks, pasta products, baked goods. So if we take the acidified casein and neutralize it by calcium hydroxide or sodium hydroxide, we get calcium caseinate or sodium caseinate. So calcium caseinate is cross-linked by calcium, and it is not truly soluble. It forms a dispersion or colloidal suspensions. It has low viscosity and it's opaque. Because of this opacity, you can use it in whipped topping, creamers, imitation of cheese, whereas sodium caseinates are formed through solution, so they are soluble, they are great for emulsification, they form viscous solutions, they're translucent, and accordingly they're used in so many different applications, infant formula, beverages because of solubility, meat products and baked products because of their viscosity and emulsification capacity. So whey protein, the ones that are used, are formed by filtration or ion exchange, have a wide range of application due to excellent functionality, solubility, gelation, even emulsification once they are denatured. And here induced browning, especially WPC because of the lactose present. So sometimes you want that browning to occur in certain products, such as vape products. Whereas lactalbumin that is produced by simply heating the whey where you form a coagulant, it's an aggregate, it's insoluble, obviously it's denatured polymers. It's greatly only used as nutritive enhancement, not much application. So I have omitted few slides, these slides were just an example of examples of research done on different types of proteins. FYI, there is no time to go through them in class. So I'm going to give you 5 minutes break, and then we'll continue with the next topic.
Sorry, I had a meeting with my research group. But should I make that up at all if I just watch the presentations on recording? No, it doesn't matter. Okay. And then I've had questions about PDCAS and just allergen stuff that I can free and ask in class. So for someone that has a PDCAS, say of like 0.5, there's a limiting amino acid. Now, if you just ate 2 servings or ate like twice as much of that, would you be getting your full amino acid profile, or is there just like the absence of a certain amino acid in there sometimes?
So, well, if there is an absence of amino acid, you get a PDCAS of 0.
Oh, okay.
If any amino acid that is essentially present in 0 amount, that means the whole protein is useless in terms of acids.
Okay.
But yeah, the PDCAS is, it tells you, yes, definitely the ratio, and then on the label, let's say, it will tell you how much you're getting in terms of daily value of the protein.
Okay.
So you might want to get twice as much of this protein to get the same amount of protein from one serving to another protein. So let's say you ate 10 grams of this protein, you need 20 grams more than protein to get the same nutrition.
So you could survive just off like one plant protein if you just ate the right amount of it to
Yeah, but then you'll have to think about calories too.
Yeah, okay.
Yeah. Like how much do you want to consume of it?
And do protein levels that have a percent daily value have PDCAS calculated into that value?
So the daily value is the PDCAS is part of the daily value.
Okay.
Because let's say you have 10 grams, but it has a PDCAS of 80%, so that means you're getting 8 grams towards the daily value.
Okay.
So you're consuming 10, but 8 grams of that is daily value.
And then regarding allergens and allergies, you said we'll probably end up with like a pea allergy if we end up eating more pea protein, or we've gotten soy allergies because we eat more soy. How come there's no like meat allergy if we've been eating meat forever? There's no like nothing relating to just those proteins.
Yeah, that's even big, but some people have beef allergy.
Yeah.
Some it's very
Or
like
like the alpha gal.
yeah. So there are some people allergic to certain sizes.
Yeah.
Oh.
But we've been eating tons of meat, but we
No,
don't.
maybe it's in our.
I asked Tonya,
nature.
and it was like, well, if you're allergic to meat protein, that's just like what our bodies are.
Yeah.
That's the protein from our muscles.
Exactly. No, that's a good.
You
Yeah,
can't destroy
destroy
our
our
muscles.
own muscles. Yes, it has to do with our genetics
Okay.
and being carnivore.
But even though like our meat industry has changed so much, it's not like the same meat we've been eating, so
No.
I think it might.
We
start
might
to go.
get growing
Okay.
to certain modified protein that we are consuming. Just like
hate opening these.
It works, that's what I do. It's half the day.
Yeah, they're so bad.
Wait, do you
I wish it was like a little bit less of an exaggeration, but I got back saying, yep, roads are slick, I'm super terrified.
I thought you were just supposed to do
I don't think they're gonna cancel class.
Oh, they just pass it.
Yeah, my partner.
Yes. Oh, okay.
I already canceled the first term class.
So like,
Can we skip and just say we're people driving and watch it after?
I want to.
Can you cancel?
I don't want it to be disgusting. Like, I don't want it to be dangerous for people to talk about it, but I want to get like
Before we start with the legume proteins, and now I'm convinced I'm behind, not my fault, your fault, no, I'm just kidding. I'm behind because they cut off a whole week of the semester, right?
Yeah.
So, in order to finish at least the majority of what I want to finish in this course, I'm gonna give you two options. Think about it, I don't want to answer today. Are you scared?
Yeah.
Yes? One option is not to have an exam, to have a final, and then use that time to finish lecture material. Or, if you want to have an exam, we will do it outside of class time. Vaidi agrees to that, although he's not taking the exam.
Except to participate.
Thank you, you're so kind. What was your, okay, I want to hear Vaidi's
Not-
opinion.
Okay.
What do you suggest, Vaidi? Huh?
Yes, person that doesn't have to take the exam, please tell us your.
Not have the exam.
Not have the exam?
Yeah.
Or,
Okay,
Will the
Kate.
final be cumulative? If we don't have the exam, will the final be cumulative?
In any case, the final is cumulative.
Would it be possible for you to record the lecture and us to watch it on our own separately?
Yeah, isn't it boring enough for me to just be here? It will be double as boring to record the lecture. I can do that, but I feel there's just not much education from doing that.
I saw the recordings from
well, what's
the
the downside of not taking the exam? Just
The
our grade is
downside
weighted
is
more.
for those of you that did not get an A last time in the test and would still like to get an A in this class. You don't want your grade to be distributed between two tests only.
What if we increase the number of participation points we get? And then we will participate more in lecture, but our grade will be weighted a little differently.
Okay, that's a good suggestion, as long as your participation is meaningful and energetic and full of love to proteins. Yeah?
Instead of doing like a full exam, could we do like an essay or something? Like a yeah.
And who will grade the essay? You?
I mean, but like it would probably be just as much effort for you to grade exams, wouldn't it? Or not an essay, but like maybe like I don't know. Could we do a take-home exam?
Oh, take home exam.
It's almost like we just not have the exam.
Jason, what do you think?
Yeah, I think-
What is your preference?
Take home final.
No exam
Cancel
takes
the
a lot of
final.
power.
Final.
Take home final?
Yeah, exam on the last day, take home final. For cumulative.
Wait, what?
What?
No, I don't think two tests on.
Wasn't there the same lecture last time you took it? I thought it was there in YouTube.
What's that? Say that again.
The same lecture was there in YouTube, which you took the same course last time.
Yeah.
And those lectures were recorded as well.
I don't mind recording the lecture. I do have recorded lectures from last year, but I don't mind recording. I just feel it's boring and you don't. I mean, it's boring as it is, me talking and you not participating and
It
not
doesn't
asking
give
questions.
an opportunity for us to ask the questions while it's happening, though. So sometimes it's hard to follow along. If I
Yeah, and I would like, I mean, when you stop participating, it's boring to you, it's boring to me, really. I feel like talking at you, which is, yeah. So, think about it. We can discuss next time. We still have one more week before the exam, supposedly. Huh? Say
What are the
that.
options again?
Well, it got lost. Not have an exam and just have a final and continue with lectures. Have an exam outside of lecture time. Yeah.
So if we had an exam, it would only be on like 3 lectures, right?
The exam will be on whatever we didn't cover last time. So enzymes, dairy, soy. I don't know what else I can get to next week. Yeah, it will be just what we covered.
Or we could throw in there take-homes.
What's the difference? Okay, let me ask you. What's the difference between take-home exam and having an exam outside of the
The amount
period?
of studying you have to do.
The amount of studying you have to do.
Yeah.
But in any case, the option was either exam in class or exam outside of class.
Oh, I
You
thought
can
we were
refer
getting
the
rid of the
notes.
exam.
Huh?
I thought you said we would get rid of
It's
the
no
exam. and
exam.
just put
Oh,
it
if you get rid of the exam, oh yeah, that's true. If you get rid of the exam, then you get rid of it, the chance of getting your grade distributed over multiple tests rather than just midterm and a final. But I'm okay with take-home exam if that's a preference. So then we have 3 options, right? Take-home exam outside of the lecture time, or no exam.
How long would we have for the take-home exam? Just a week?
Huh?
Would it be a week or like the next day for the take-home exam?
Oh, I have to think about it. Maybe a week. Yeah. So how about each one of you send me an email with your choice, one of the 3, and I will tally.
Are the grades entered in for like our practice problems?
Oh, if you turn it in, you get the grade.
Oh, okay.
I turn it in completed, so you get the grade. Yeah. Good. So, before I start here, I wanted to do discussions of the practice questions that I posted online. So I want to divide you guys in half again. We'll do about 10 minutes discussion, and then we'll start a new topic. All right, just to change up a little bit. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. Divide into half. The first half here, do the first 5, and the other half, do the second 5 questions. Talk about them, and we'll reconvene as a group.
You're fine. I feel like I yeah, it depends on that.
Yeah. Okay, so, wait, are we doing that first?
We're doing the first one.
Okay. Favorite first deal.
I just think like a business, maybe not like very crazy. I said like. Like
I think there's a reason. You guys just said, it's just mainly he's in the case. He's unstable, listed. We still listed, and it is custody. It doesn't say house. And it just says bedroom. It's not necessarily. Makes it better, more
Second question, no, the slide, yeah, they're asking the last
No, I think it's asking like, why? But at 1% maybe
Yeah, whether we want to do diversity or, yeah.
Are we on the
just said it was low viscosity.
So if it's going to be a rate, we can develop that.
So 11 out of 2 percent.
You have to go for protein which is resistant to each one.
Also on the previous slide, I think there was examples that had good color. It was opaque. It was good. Yeah.
Well, you could say both. If you wanted to do carbon 4%, at 9%, or you do 1%. Yeah.
They didn't tell me the calculations. They just like, go make it. And I'm like, okay.
Yeah, and then acidifying calcium and phosphate precipitate for myself and gas. So it was in
Oh, it's different.
All right, are we ready for discussion? Not yet. Couple more minutes. 3-4 more minutes. They want more minutes.
Well, that's why we confuse each other. Yeah.
So who's presenting next week? Are you guys?
Going back to
You're
day
presenting
one.
next week? Did you send me your final papers?
It was like either last week, we were a little late on it.
You did send me the 2 articles? Okay.
I didn't get a response.
That's okay.
Maybe I didn't open the email. I'll check.
I just assumed they were okay because you didn't.
Didn't we discuss them?
We had discussed them at our first meeting, and you had said that you liked both of the papers.
Oh, no.
Or no, we had presented you with 3 papers, and you liked 2 of them. You were kind of iffy on one of them, and you said as long as we could make a good story out of it, and then we did some more searching, and then we decided to do those 2.
Okay.
So we didn't really change it.
So for the evaluation, you said fill out just the part, the presentation, or the presenter part, or just the principal thing?
No, fill the whole thing from your point of view and just write your name down there.
Okay.
Because your grade will have 25% weight.
Okay, gotcha.
So you need to fill everything.
Okay.
But if you just create a new, that is so
Should we just write our vote for example after this?
No, just email it better to me. I don't want anybody to be pressured, peer pressure. Just send me your own confidential vote.
Sorority, we would say eyes closed, hands up, and so you voted, so everyone's hand was actually here, and then if you wanted to vote for that option, then you would just click in your hand and then vote it.
Oh, so it's anonymous too, because everybody closed your eye, except if you peek.
Except if you peek.
Okay,
And then you get that one.
so this group here, you did the first 5 or the second 5? First 5. Okay, let's start with the first one. I'm not going to read. I assume that you have all of this in front of you. So, tell me what you thought and give me your justification as a group. You can have a designated person for each question.
Okay, so for the first one, we said casein because amino acid sequence contains regions of hydrophobic and hydrophilic patches, making it a good emulsifier and foam former.
Which form of casein?
Sodium carbonate.
Sodium caseinate? What about the browning color? What?
So it's like now we choose calcium.
No. What we just said about, huh?
Is browning okay, because you're just bakery?
You just what?
Is browning just okay? It's not a cleaning bad.
It's not. You want a nice, pleasant brown color.
Oh, it's okay.
From the Maillard reaction.
Yeah.
Can you use miso?
Whey protein in this situation, WPC. In this situation, WPC that would be denatured will form a nice film, a good gelation, gelling agent, because you want the gel in the sponge cake to form, because sponge, it's mostly you're holding a lot of foam, so you really want a really nice strong gel to form upon baking so that it holds that air. So WPC, film forming, good gelation agent, and browning due to the lactose present. Okay, the second one.
Now I'm nervous to answer. Whey,
Okay.
because the globular structure makes it highly soluble within a liquid, and it can, like when it's heated, it will partially denature to add strength and help with a little bit of the gelling without making a very strong, thick gel.
Okay, in a gravy, do you want to form a gel or do you want it to be viscous?
Okay, we talked about this too, and I said I want it to be as runny as possible, but everyone else disagreed.
So you want it to be runny, viscous, or gel? There's three different things.
There's different preferences.
Yeah.
Usually gravy, it's not runny and it's not a gel, right? It's really thick, huh?
Yeah, it's really bad gravy.
Okay, what the good?
I think it.
Ideally, you don't want it to be runny water. That would be gross.
I like it that way.
And then we don't want it to gel on you. That's even more gross. So you want it to be a little bit with a texture that is a little bit viscous. That's my understanding of a gravy.
So sodium caseinate.
Sodium caseinate is what it builds nice viscosity. Yeah, that is one main thing you want in your gravy. You don't want it to form a gel, and your whey protein will form a gel when heated and reheated. Yeah. Okay. Let's see your third. Third is a charm. Katie might want to tell us.
We said calcium case.
Yeah, right on.
Yeah. Because it's more heat stable and it's opaque.
Yeah, and also it helps with increasing viscosity too. All right. Good. The fourth one.
Can I ask you a question?
Yes.
You remind me of the relation between viscosity and like emulsification. Because back to gravy, I'm thinking I don't like seeing like back up, really separate from the water.
Yeah, the caseinate will help with the emulsification as well. So yeah, emulsification, the caseinate can help with that. So not to separate the oil. At the same time, interaction with water gives you also the continuous phase becoming viscous.
Oh.
So you have the viscosity of the continuous phase and the emulsification to entrap that oil and not having it separate. So thank you for bringing that up because you definitely don't want your oil to separate. Okay. 4. What do you think, Becky?
We said whey because it's stable at that pH.
That is correct. It's soluble and stable at low pH.
Is it true that it's also colorless at those lower concentrations?
It is colorless at acidic concentration as well. Yeah, acidic conditions. Correct. Now the last one here, number 5 for you guys, is tricky. What did you come up with? We'll leave that to Vaidi.
Acidified casein.
Acidified casein. That is the first natural answer. Why do you think so?
Because the minerals
Leached out. Yes, that's the most logical answer, but you know that they acidify the casein with mineral acids. So then the ash content becomes high. This is a tricky one. You wouldn't have known that. You would think that acid casein based on the exact reason you said. But because they are precipitated with mineral acids, then they don't do that. They go ahead and use rennet casein because overall it has lower ash content. Okay. All right, let's move to the next group. What was the answer for the muffin question, which was among the questions we had at the beginning of the class this semester? Nina.
an open structure, so it's a natural emulsifier, and then since the batter is emulsion, it's viscous and it's cohesive.
Very good. So sodium caseinate has good emulsification properties, good for batter consistency, it has high water binding capacity, gives you softer, moist muffin. It has bland flavor, builds structure. Okay. Alrighty. There's some calculation there. Yeah, still waiting. Yeah, go ahead.
Whey protein, just because it's soluble and stable at low pH.
Yeah. And then in terms of usage level, what did you come up with?
If we were using whey protein isolate, about 5.4,
Yeah,
assuming the isolate's at 90%.
yeah. Good. And if you say WPC, which also can be used assuming an 80% protein, then you would use about 6.1% because you have less protein. Okay, next. The hot dog thing. So, what functional properties did that whey protein bring in? Huh? Water holding, angulation, what else? So definitely help with binding water and fat as well, and increasing viscosity when you heat it. So, and form irreversible gel when cooled. Okay. List an alternative milk protein that could be used in the above hot dog formulation. So it doesn't mean that that's the only protein that you can use. You can use another one, which we said is already, what did you say? Sodium caseinate. Yes, it's another emulsifier and it can also bind water and builds viscosity. But it doesn't form a gel upon cooling. All right, so the last one. Excessive protein hydrolysis. You want to break down the protein to break down more than 80% of your peptides. Unfortunately, to eliminate all of the potential epitopes. That makes it taste horrible. Okay, good. Keep you 15 minutes and then I'll let you go. Okay. So, moving on to legume and oilseed proteins. So, I'll give you an overview of this category, but focus mostly on soy protein, given its the knowledge that we know about soy protein being researched for over 50 years and a lot of applications. I don't expect you to know this yet, but maybe you do. People from my lab might. All of the above? Two of the above. A and B. C is not correct. Based on research we've done in our lab with Jordan, Walter, then Chelsea, we found that both glycinin and beta-conglycinin are allergens. And there are literature to prove that as well, not just from our lab. But we'll talk about these different proteins in more detail, obviously. Glycine and beta-conglycine are globulin proteins. They are storage proteins. That means the plant or the seed store these proteins for energy. And then these storage proteins are the proteins that are most influential or responsible for the functional properties of soy proteins. That is correct. We'll talk more about that. So, in fact, glycinin is an 11S legumin, the type of a globulin, plant globulin protein. And beta-conglycinin is a 7S vicillin, another type of a globular plant protein. From this nomenclature, this means that glycinin has higher molecular weight, beta-conglycinin has lower sedimentation coefficient, glycinin has higher sedimentation coefficient. Do you know anything about sedimentation coefficient? Have you heard about it before? Fan, you did? You're nodding yes or nodding no?
Yes.
Okay, what is sedimentation?
It's because of, if you use for example, the centrifugation.
Yeah.
And it's will become more, for 11S, it's more like higher sedimentation coefficient, but 7S is lower one. I don't know how to
Yes. You're right. Sedimentation coefficient is the ratio of the particle sedimentation velocity, how fast it will sediment, in relation to the acceleration, the speed of the centrifuge, how fast that's the centrifuge and the gravity of that pull. So the higher the number, that means it will sediment faster at lower acceleration. Okay? That means if the protein sediments faster, that means it has higher molecular weight. It requires less force to pull it down out of solution. It's large molecule, it will sediment more easily than a smaller molecule. So 11S has a higher molecular weight than 7S. Beta-conglycinin has a lower sedimentation coefficient. 7S is lower than 11S, and S is the unit for sedimentation coefficient, or not unit, the abbreviation. It is the units is per time. And then glycinin has higher sedimentation coefficient, so all of them. So these are the different classes of legumes, oilseeds, and legume/oilseeds. Camelina and pennycress are not legumes. Why do I have them here?
I don't think Silphium is either, is it?
Huh?
Is Silphium?
And not Silphium either. Okay, ignore this. This should be over here. It just hit me. I don't know why. Okay, so anyway, non-legume oilseed. So these are oilseed, not in the. What's the definition of a legume? Yeah. It is nitrogen fixing, but what is also characteristic about the plant itself? That we associate a pod with beans in it as a legume, right? Yeah. Okay, so oilseed, meaning it has high content of oil. So, and most oilseeds have high content of oil as well as high content of protein and no starch. So, cottonseed, rapeseed, another rapeseed is also known in the northwest or Canada as canola. It's the genetically modified rapeseed. Sunflower, coconut. So these are in that category. Legumes that are don't have high amount of oil. So you have the common beans, the peas, lentils, chickpeas, or in other words, pulses. Okay, so these are high in protein, well, relatively high, not very high in protein, but relatively high in protein and starch, low in oil. Oilseed legumes, soybeans and peanuts. Forget that I have this here, not here, here. So these are common. They are both, they fall under the legume category, and they are oilseeds because they're high in oil, in protein, in fiber, no starch. Camelina, Silphium, and Pennycress, these are mostly weed crops. Now they're being developed as crops for food, but there are also oil seeds that are high in oil, high in protein, and they are being developed because of environmental benefits as well as their potential dense nutrient content for food use. Okay. So here we can see the distribution of the composition of the different types of legumes and oil seeds. So if we look at the pulses, dry beans, lentils, peas, fava bean, chickpea, you can see that it's mostly carbohydrates, starch, and fiber. And the protein content is around 20-22% on average. Whereas the oil seeds crops, if looking at soybean in particular, you have lower carbohydrate and it's mostly fiber and small sugars. And then a lot of protein, about 40% on average depending on variety, and quite a bit of oil or fat content. So we don't care about carbohydrate and fat for this class, although they're valuable components. So we're focusing on plant proteins. So plant proteins in nature is mostly globulin proteins and albumin proteins. And globulin represent the majority of the proteins, and they are known as storage proteins. And they're responsible for the functionality of the protein and the nutritional quality of the protein. Whereas albumins, they're very heterogeneous, made up of so many different proteins, and they are mostly enzymes. A lot of enzymes are albumins. They are some structural proteins. They're highly soluble, and they can form complexes with carbohydrates and nucleic acids. We don't care much about them. We care about the storage proteins, the globulins, because these are the proteins that are most abundant and contribute the most to the functionality that we care about in food systems. So globulins have two main subunits or families. You have the legumin family and the vesicolin family. So the legumin is also known as 11S, forget about glycine here for a second, is 11S, and vesicolin is 7S. In soybean specifically, the 11S is glycine and the 7S is beta-glycine. But in pea protein, for example, it's not glycine and beta-glycine, they are just referred to as legumin and vesicolin. Okay, so like I said, these are the functional proteins. They are responsible for the functional properties in food. And they are kind of divided into fractions based on sedimentation coefficient. So we can still have 2S within this category, and these are low molecular weight trypsin inhibitors. They are fragment resulting from dissociation of a bigger molecule. We learned that these types of proteins exist as a quaternary structure. So they exist as a bigger molecule with several subunits, but under different conditions of pH and temperature and ionic strength, these subunits can be dissociated, and when they dissociate under certain conditions, they might exist as a separate unit, but of 2S. 2S, that is, they sediment at higher acceleration force and low speed of sedimentation because they're small. We have the medium size, which in general is your vesicolin, and then the high molecular weight legumin, and under certain conditions we might have association into bigger molecules, bigger polymers that can have a sedimentation value of 15S. So that it could be an aggregate of 2S, 7S, or 11S, or a combination. So different varieties, different species even, have different ratio of legumin to vesilen. So for example, in soybeans, you have higher ratio of legumin to vesilen compared to beans. In beans, you have more vesilen and less legumin. So if you look at the ratio here, it's 0.5 to 1.7, 11S to 7S. Whereas in beans, you have less of the 11S and more of the 7S. What does this imply? It impacts the functionality of these proteins. So for example, in peas, you have lower ratio of 11S to 7S than you have in soy. What does that imply? We will learn that 11S is better for gelation and vesilen 7S is better for emulsification. So for example, then soybean protein has better gelation properties than pea protein, given that we have higher legumin to vesilen ratio. So yes, we will learn that this has better emulsification, this has better gelation, it's a bigger molecule, it has SS linkages, so it's better for gelation than emulsification. We will learn that beta-conglycine or vesilen, they have better balance of hydrophobic and hydrophilic residues on the surface, so they can form better emulsifiers. So both legumins and vesilen, they are oligomers. That means subunits are they form to form a big polymer or oligomer. And so there is several subunits within 1 mole of protein. There is high percentage of hydrophobicity or hydrophobic amino acid. In soybeans, globulins, over 40% of globulins in soybeans are hydrophobic amino acid. Over 40% of the total amino acids in soybean are hydrophobic amino acids. They're also high in acidic amino acid, mostly aspartic acid. And you will see that subunits from legumin, we have acidic subunits and basic subunits. Acidic subunits are obviously called acidic because they have high percentage of acidic amino acid. We have high homology in amino acid sequences. What do we mean by homology? We have similar sequences that repeat within the different subunits. So they're very closely related. Okay, speaking of homology, when we say we have allergenicity to soybean, but we have no allergenicity to pea protein, well, that is not going to be the case for long because there is very high similarity in amino acid sequences among legumins, even within different species, among vesilen within different species. Because of this homology, there could be cross-reactivity. If somebody is allergic to soy, might be allergic to pea. And there's a lot of also cross-reactivity between soy and peanut, for example. Both are legumes, oil seeds, both have legumin and vesilen, so there is high homology. For example, the research that Chelsea and Jordan in my lab did, we needed serum from people that are allergic so we can get antibodies to do our in vitro testing. We were able to obtain serum from people that are allergic to peanut because they were more readily available, and it was so hard to find serum from peanut protein allergy. But in any case, these antibodies that we were able to obtain also reacted with soy protein. So we were able to develop our assays just because of the homology. That means similarity in amino acid sequence between legumins and vesilen across different species. Molecular structure and ratio determine functionality, and we'll talk more about that next time. But please do send me email with your vote of what you would like out of the 3 options. What were the 3 options? Huh? No test.
Making a movie.
Huh? Making a movie? Making a movie, option number 4. No, seriously, no test, take home exam, or exam outside of lecture time.